So today, okay, we'll start with a new topic, what are called unitary transforms. So now, so it's a kind of a shift, okay, between whatever we've been doing till now. It's a big shift now, okay, from let's say what we did till now. And this unitary transform business is about. So, for example, right, one special unitary transform is actually a DFT. Okay, which is something that you've all done at some point or the other. At least a 1D DFT you've all done. Okay, 2D DFT I do not know how many have done it, but 1D DFT all of you have done. Now, so for example, right, there are kind of say several of them. Okay, DFT is just one. Then there is something called a DCT, a cosine transform. Then there is something called a discrete sine transform. Then there is Walsh-Hadamard transform. There are so many of them, right, that come under this. Instead of right, taking let's say DFT and then DCT separately, right, one at a time. Okay, instead of that, okay, you could also do it. I mean, it's up to how they teach. Okay, so the way I see it is, I would rather kind of create an umbrella of umbrella that talks about unitary transforms in general. Okay, and then right after okay, we have a framework like that, then we would like to go and check out each one of these. So in a sense that the framework will be kind of common, and then each one of these will have some special properties. I mean, they'll have an affinity for certain kinds of matrices and so on. So for example, DFT, I told you, okay, when we actually did that LSI LTI system matrix. So at that time we said that it can diagonalize a circular matrix. Similarly, right, I mean a DCT, for example, if you look at a Markov kind of a process, right, you can show that a DCT is more optimal, not optimal, is superior to a DFT and so on. So in that sense, right, each will have an affinity for certain classes of kind of data, and either you kind of see it from that point of view, from in terms of data, or you see it in terms of what it can do to a system matrix and so on. So it's a kind of a fairly wide thing. Okay, we'll try to do what we can. Okay, and the idea would be to sort of create a big umbrella under which each one of them can be just examined as special cases, which will make it easier. I mean, and there's a nice sort of a structure to all of this. We will be kind of missing all that structure if I simply wrote down an equation for DFT and said, right, this is a 2D DFT. Now, instead of that, if there was a natural way to get on to a 2D DFT from a 1D DFT, okay, that looks a lot more nice. Actually, that structure exists. Right? It is for us to explore it or not. Okay, so I thought what we will do is we'll kind of go from what we already know in terms of 1D unitary transforms. Then we will see how there is a natural vehicle, right, that takes you from a 1D transform to actually a 2D transform, which will also set the stage that tomorrow if you have to do a 4D transform, right, you'll automatically know what you should be doing. Okay, so once you know from 1D to 2D how it goes, then 2D to 3D or 3D to 4D, okay, it depends upon what you want to do, but all of that, right, will look kind of straightforward and look like just one step away. Because that structure is all inbuilt, okay, which will be kind of sort of stupid to miss. Okay, so we'll kind of go like that. First of all, right, when we talk about actually, right, the real topic is image transforms. I put this in bracket. Okay, so basically about image transforms, and mainly it is about unitary transforms. So first of all, right, why do you think that people want to even go to a transform domain? Why does one take some data and then do some transformation on that? So why study, let's say, right? Why should I kind of transform data? Assume that whatever, right, you have an image or a 1D signal, speech or whatever, it doesn't matter. So why should I transform an image or transform an image or transform a signal, let's say. Let's not put 1D, 2D. Why should I transform a signal? There must be different reasons, right? One reason, what is that? So spectral information. Okay, so in a sense that's like an alternative interpretation, right? So you see the signal in one domain and then you see it in another domain, and that seems to reveal things that are not kind of directly revealed in one domain, right? It's like an alternative interpretation it's like an alternative interpretation, okay, that actually that reveals new information. New in the sense that reveals novel information, let's say. Okay, nothing new, because whatever is there in one domain is exactly what is there in the other domain, but something that makes it interpretable, that makes it easier. Okay, so which is why I wrote interpretation. So maybe your interpretability becomes kind of better, right? Rather than then what are the other reasons?
So operations are simpler in the other.
Operations are?
So operations may be simpler in the other.
Okay, like for example.
Can be interpreted as
Exactly. So not only maybe simpler, but even faster maybe, right? So one could be a computational speed up. Right? You might want a computational speed up, similar to the case that we have. So instead of doing a convolution in time domain, you may just go use the FFT, right? Compute the DFT and take the product and take the inverse. That's faster. So computational speed up. Okay. So for example, right, FFT for the convolution is one example. That's okay. I mean, right now, if you just even if you talk from in terms of Fourier transform, that's fine. Then maybe noise filtering or something, right? Like for example, you could have a signal that is getting superimposed with some sinusoidal noise, and so on. Like for example, the 60 hertz fluctuation that we have, right? These are all easily kind of determinable, because once you go to the Fourier domain, you know that it exists at that frequency, and therefore, right, you can have some kind of a filter that can remove it. Or even in general, right, when you want to do noise filtering, what do you kind of typically do? You may want to go either for example, if you know where that frequency is occurring, it makes it easier. Something like this, electric supply fluctuations and all. Sometimes, right, it may be just some other random kind of noise, in which case also, right, you may want to do some filtering, and perhaps the filtering becomes kind of better if you go to some other domain. Noise filtering. Then what else? Anything else that you can think of? I have a few more things here. What about compression? The compression in the sense that, right, you go take, let's say, a Fourier transform, and then you realize that some of those coefficients can be actually dropped, right, in the sense that, and then you take the inverse, you look at the image. So it's like saying, right, it depends on the application. If you have an application where, let's say, you are extremely sensitive to what is there in the image, maybe you can't afford to drop too many things. But if you feel that only some certain information needs to go, and that anyway can be conveyed, even if I chop off a few things, right, then you can save what you send, right? So basically, compression is one thing. Of course, it's not the same as doing a compressive sensing, right? There you only sense what you need, whereas in compression you sense a lot more, and then you sort of sit back and worry about what can you throw, right? So ideally, we should know how much to sense, but then most of the time we don't know how much to sense. Right? So we just sense whatever we can, and then we kind of worry about. Then we go to a transform domain. Then we see, okay, what can be thrown off. Then anything else? Compression. So let's say some of the insignificant, in the sense that what is insignificant for an application. Okay, it doesn't mean that always you can do that. So some coefficients can be. When I say coefficients, those are in the transform domain. Okay, some coefficients can be kind of thresholded, right? In the sense that you can simply remove them, okay, and then kind of say that the image is still reconstructed fairly well for my application. Then there is one more reason, okay, what is called sparsity. Okay, so for example, sometimes if you look at the image, sort of the representation, right, it might actually so happen that in one domain, for example, right, let's say when you see the image, right, it looks like right, there are so many coefficients, everything looks important, all these n square values that you have, right, on the grid. But then if you were to take a wavelet transform or something, right, then you will suddenly find that right, it has a sparse representation there. Sparse in the sense that a few coefficients sort of seem to tell the whole story, right, and then which means that a lot of energy gets packed in simply a few coefficients. Another example would be like to kind of go back to what we did yesterday, right? Like we said, on the one hand, you have a space variant blurred image for which you can ask for a PSF at every location. Instead of that, a sparse representation would be to go to the kind of motion space, right? The pose space where you know that the camera has only gone through some 5 or 6 poses, and then say that, right, have an L1 norm there, and say that solve for the poses rather than solve for each of the blur kernels, right? I mean, just giving an analogy, because that is something that we did only recently. Right? So sparsity again means that, and apparently natural images have the sparsity in some transform domain or the other. Wavelet is something mostly people find that natural images have a sparse representation, but then there are so many others, contourlet transform, curvelet transform, so many transforms that have come up, wherein for certain applications they will have a very nice kind of a sparse representation. Depends upon again your application. Okay, so the idea is that, and of course, then there are others, But anyway, so the main things are these. Okay, you can of course add on a few more. Okay, now the way, right? I would kind of I would like to uncover a cover, whatever you call that, right? Would be to kind of look at it, right, in terms of in terms of, under kind of three heads. Okay. So first of all, right, let's kind of look at what do we mean by a data independent transform versus, because for me to write those three heads, okay, we have to first kind of look at what do we mean by data independent transforms versus data transform versus a data dependent transform. Data dependent transform. So for example, right, when you kind of apply a Fourier transform on a sequence, let's say, right, suppose I have a sequence U, which is like which has a length n. Okay, let's say U0 to Un minus 1. Now when I kind of apply a Fourier transform on this, that's like equivalent to applying a DFT matrix, acting a DFT matrix on this in order to give me a V. Okay, V will be this DFT coefficient, which in general is complex. Now, we don't really worry about what is U, right, when we apply phi. Okay, you give me any U, once I made up my mind that I want to use a Fourier transform, I don't really worry what is this U. For example, if you think of it as an image, right, for an image you have to kind of write it in a slightly sort of a different form, but just to kind of, just for the sake of this one motivation. So for example, if I knew that it was a face, right, I don't change the basis. Or for example, if I knew that it was a class of tree, so if this image is coming a priori, suppose I knew that, right, it's actually a tree, I don't actually use that knowledge at all. I simply say, right, it's going to be still the same Fourier basis. It's standard, right? You don't change the basis. You don't care what is the input signal that is coming in. In a way, it's good because you don't have to worry every time as to where is the signal coming from, what is its origin. Right? Whatever be it, we simply have this kind of data sort of an independent transform, which is like a DFT, or if you feel you want to use a DCT. But on all of those, the basis that you choose is completely independent of the signal. You don't worry about what the signal is. In some cases, right, you can show that if the signal happens to come from a certain class, then maybe this transform that you're using, even though it looks like it is data independent, but then it could turn out to be optimal for that class. Okay, this is something that we will look along the way. Okay, but normally, right, normally we don't really worry about where that sequence is coming from. We simply apply. Okay, so all your DFTs, DCTs, they all come under this. Okay, DFT, DCT, and all of this, we don't look at the data and sort of make up the basis. Right? We don't construct the basis by looking at the data. We construct the basis independent of the data. Right? So DFT, DCT, DWT, okay, whatever, DST, you name it. Okay, all these, right? These all come under what we would call as data independent transform. So right, it has its advantages because it's completely independent of data. So the bases are known a priori, right? So for example, if I know that, right, I'm going to use a Fourier transform, then the other guy, I don't even have to send him this basis, because he knows that if you're saying DFT, then it means that he knows what is the basis that you're going to use. So the bases are kind of constructed or known a priori, known, whatever you want to call it, a priori. Okay, independent of the data on which the transform acts, independent of the data on which the transform acts. So in a sense, it's good. Okay, and as we know, right, a lot of the things that are happening are all with respect to independent transforms only. Okay, very rarely do we do a data sort of a dependent transform. But you might ask, then why does it even exist, right? Why should you have something like a data dependent transform? The point is, right, data dependent transforms, these are seldom used, okay, in reality. So for example, because every time if you have to construct a basis, it is going to change, right, depending upon which class of data is coming in, that it means that the other end, that guy has to know what it is. And again, right, you might want to add few more examples to the data, in which case that basis will again change, right. I mean, for example, if you had whatever, right, 1 lakh images today of that data, tomorrow you have, let's say, 2 lakh images, you might say, I want to refine the basis now. So all of this is like an incremental process wherein you can keep on changing the basis, and then right, then it makes it harder, because then at the other end, right, you have to kind of keep updating the basis and so on. Therefore, this is seldom kind of used. Okay, not that, right, I don't mean that, right, nobody uses it. I mean, again, right, I'm going to show you applications where data dependent transforms play an important role. The saying seldom used in the sense that if you're going to say looking at transmission of these coefficients and all, seldom does one use a data sort of a dependent transform. Seldom used in that sense. Okay. But then one of the main uses, right, has been that, so for example, right, there is one transform which is actually a data dependent transform, which comes under the name of KLT, what is called a Karunen-Loewe. So it is like Karunen-Loewe transform. So what is called the KLT. This also comes under different names. It's called the Hotelling transform. It's called the PCA. Some people call it PCA. Right. So all of this means the same thing. Hotelling, KLT, Karunen-Loewe, PCA, they all mean the same thing. Now this transform, mother of all transforms, in the sense that, right, then you might wonder, I mean, what is that? Right? So actually, right, what it means is that this transform, right, is kind of optimal in some sense. Okay. And the whole point is, right, when you say that something is optimal, right, then that optimality has to be with respect to some data. Okay, it's not like so this optimality notion, right, rests with so this optimality, right, so this kind of rests with the underlying this notion rests with the underlying data distribution. Okay. So now the point is this, right? So what this means is that when you are applying a DFT or a DCT, or for example, right, some other transform which is actually data independent, right, you might want to kind of ask, is my transform optimal? Okay, generally you don't ask, because first of all, you don't even know what does it mean to say that something is optimal. But then this guy which is sitting there, the KLT, kind of can be looked upon as kind of a benchmark. Okay, even though right, you may never use the KLT, okay, but then what it actually means is that, right, you have the KLT sitting right there at the top, right, being optimal for that kind of data. Again, right, this is all data specific. When you say optimal, it is for that kind of data, which is why I said it is for a distribution, right. So for example, it could be for faces, right, what could be the ideal kind of a basis that you should be using, or for example, if you look at natural scenes, again, right, so what kind of an ideal basis should you be using? So in that sense, it's sitting right there at the top. Okay, and even though you know that using that itself is going to, even though you know it may be optimal in whatever sense, but then using that is not easy. So instead of that, what you say is, okay, now for this data, if I use this DFT or DCT or whatever, can I at least check how close am I to this guy? Because if I have 3 or 4 of these data independent guys, and in some sense, and if I can show that one of them is actually closer, then it would mean that you would rather use that, right, than kind of use some other data independent transform, because it already gives you an idea that you are kind of close to it may not be the KLT, but then it is kind of close to the KLT. And then there can be situations where a data independent transform becomes the KLT. Okay, so in that sense, right, there's also a bridge, right, which can actually cross over. You may think that you may not know, but then you can actually find out, determine that in some cases, in some special cases, what might happen is something that looks like data independent becomes the KL transform for a certain type of data. Okay, again, it's not like, right, KL transform, when you talk about KL transform, there is again a data specific. So for example, right, you might want to look at a covariance of a certain structure as an example, right. So you might want to say that for that kind of a covariance matrix, see, for example, you must have done a Markov process and all, right. So right, those guys have a structure, and we know that most natural scenes follow that kind of structure. It may not be exact, right. Nobody is saying that everything is strictly Markov and all. but we know that something would depend on its neighbors, and therefore, right, we have a certain sort of a correlation. Now, when you have such a matrix, right, which actually encapsulates what happens in a real data in a sort of a statistical sense, right, this is more in a statistical sense. So in that statistical sense, right, what you can now sort of see is that if you try to employ, right, for that kind of a data distribution, if you try to use a DCT, for example, you can show that a DCT can come closer to a KLT, in a sense that you will have a basis for actually DCT. You can actually construct a basis corresponding to this data, and you can show that which is supposed to be the KLT basis, and you can show that these bases look very similar. They may not be exact, but you can see that this guy is looking very, very close to that. Okay, so which means that you get a sense for how close you are so among these transforms, even though these are all data independent, but then some of them could be very good in terms of being used versus someone else. So how do you pick, right? So in that sense, a data sort of a dependent transform is something that we use to do the benchmarking, right? Even though this by itself we may not use for transmitting or anything, but then it serves us as a nice benchmark. And the other thing is because it is based upon the statistical nature of data, it is also used for many filtering applications and all, where you learn collectively, right, what kind of statistics a data has, and therefore, right, even this noise filtering and all that we're going to talk about, you can actually do it in a sort of a statistical sense, what are called eigenfilters and so on. So in that sense, right, I'm just saying, when I say seldom used, I mean for transmission and such, right, and such cases, but then but then it does find applications elsewhere. Okay, so but our goal, I will also I will also try to see if I can throw up a few applications of the KLT or the PC or whatever. Of course, I'm sure you've all heard about the eigenphases, right? That came up like 20 years ago. It didn't go too far. That is a different issue. But then that was the first time when somebody said that somebody did face recognition, right, without using the geometrical features of the face, but rather something which is actually statistically derived. And those eigenvectors, right, they could show that they capture whatever, right, different features of the face, and the linear combination of those could kind of help you reconstruct and then do face recognition and so on, right? So in that sense, it has been around, okay, and it still is there, okay, and again, right, in fact, I'll show an application where, let's say, nothing else works in the sense that whatever we tried, right, I'll show an application where only a KL transform works, okay, because it only understands what kind of data is there. None of your other techniques will work there. Okay, so again, I'm saying, right, so this guy is kind of say special. So basically, we should not underestimate it. Just because we don't end up using it, it doesn't mean right, it's not strong enough. Okay.